Okay, so here are graphing equations. In this case, our parent function, or mother function, is y equals the square root of x. And so we want to start by graphing just that simple y equals the square root of x. So notice they've plugged in perfect squares for your inputs. That's great. You want to work with the system to make the number crunching easy because the square root of 0 is 0. So that's your y. The square root of 1, when I plug in 1 for x, the square root of 1 is 1. I plug in 4 for x, the square root of 4 is 2. The square root of 9 is 3. So I'm going to plot these points now. And there we are. So there is the y equals the square root of x function. But that's not the actual equation that they wanted us to graph. But we're doing good work here with what we're doing. There's two shifts that happen. The shift that happens directly to the x is a left and right shift, but it's opposite of what you'd think. Plussing 1, I usually think of going to the right. It's actually going to be left 1. And then what's outside of this, or what's outside after x is directly shifted or not shifted, but what's outside of the square root here is an up or down shift. And it literally is what you see. So when I think of shifting up or down, I see a -4, I think down 4. So what happens outside is a literal up or down shift. It's literally down because it's negative, whereas the shift left and right is opposite of what you would think. This sends it to the left. So now I just take each point here that I've carefully graphed and I move left 1 and down 4, and left 1 and down 4, rinse and repeat, something like that. And so this is my new function. Now the x values are the domains. So my x's have to be greater than or equal to, now not 0, now it's -1. And if you think about it, if you put a -1 plus 1, you get 0. You can actually square root the value 0. The range is all your y values. It looks like y hits -4 and then it goes up from there. So y is greater than or equal to -4. There we are. Bada bing, bada boom. Number 17. All right, so if I make a list of what's being done here, we undo PEMDAS backwards. X is getting subtracted by 2, but it's in the parentheses. So I'm going to undo subtracting 2 last. X is getting cube rooted. And then X is also getting multiplied by 4. So I have to undo from the bottom up. So I have to undo multiplying by 4 first. So I have to divide by 4. So I get the cube root of x minus 2 equals 5. So then from there, I have to cube. So I get x minus 2 equals 125. From there, I'm going to add 2 to each side. So I've undone these things from the bottom up in that order. The answer is x equals 127. Now over here on number 18, I could really just cube both sides. So that way I'm doing the same thing to the left and the right side, and cubing undoes cube rooting. So I just get 8x minus 21 equals 10x plus 7. So the fact that they both were getting cube rooted, or raised to the 1/3, is a big deal. That made this problem a lot easier. So we get x to one side. I'd address that right away. So I took away 8x, which left me with 2x on the right side. Subtract 7, you get -28 equals 2x. So you get x equals -14. There we are. Chapter 8, state the domain and range. So the domain is all the x values, and it looks like it's going left and right forever and ever. So that's all real numbers. The range, though, it doesn't look like it's, see how it's really tapering off here, folks? It's really sitting on that line. It doesn't actually touch that line. The asymptote will be right next to the line, but the pen was thick. So the range doesn't actually get to 2. So it looks like the y's have to be greater than 2. And we'd call this also, they might also ask sometime if there's a horizontal asymptote. And it would be the line y equals 2 then. And asymptote is the line that the graph approaches but doesn't quite hit, like a limit. Here, they gave us a hint to use this thing. Make sure you know when to use that equation. You should probably put that in your note sheet. That's when we're compounding things more than just annually. So $1,500 is invested. That's my A value. At 8%, that's my rate. However, take your percent and divide it by 100. So I'm actually going to plug 0.08 in for R. It's compounded monthly. That's your end value, the number of times it's compounded. And monthly means, well, there's 12 of them in a year. What's the balance after 4 years? So here we go, 1,500 parentheses 1 plus 0.08 divided by 12 raised to the 12 times 4. By the way, if you're going to do this all in your calculator at once, make sure that you put this in parentheses. Otherwise, they'll just think that you're raising it to the 12 and then take that whole answer and multiply that by 4, when you really want to raise it to the 48th power, the power of 48. When you do this, folks, you should get $2,063.50. You bought a new computer for $2,000. The value of the computer decreases 15% per year. Write an exponential model that represents the value of the computer. So it's decreasing. So initial investment, if you want to call it that, is $2,000. You're losing 15% every year. And I don't think it tells us how many years we're actually doing this, so it's just going to be T. Now, if we knew how many years we had the computer, we could plug in the year for T and calculate. Simplify this. So in this situation, you can treat E as like a variable. But before we get there, folks, this says 24 divided by -3, which is -8. Then move to the E's with powers. When we have the same base that are getting divided, we subtract the powers. So that's going to be e to the 3. Simplify. Now here, folks, before we do anything else, we should sprinkle this power of 2 into the parentheses. So that gives us 2 to the power of 2, which is 4. E to the 10, when we're multiplying, I'm going to show you this. I was going to do it earlier. Up top, we were dividing bases, so we subtract the exponents. Here we have an exponent to an exponent, so we are going to multiply exponent to an exponent. That puts me on E, so we drop it down a level. We're going to multiply those exponents together. That's how I got 10. No sprinkling to do over here. We just have times, because there's a multiplication dot right there, and then I have -3 and e to the -4. So now you could, there's this intermediate step that you can do if you're getting confused on this. I'm going to rearrange all the multiplication. I'm going to put the plain old numbers first, then I'm going to put the e's with their powers next. This says -3 times -4, which is -12. Now here I am multiplying the same bases. I'm taking e times e, but they have powers. So when you multiply the same bases together, folks, you add those powers. So that's going to become e to the 6. Log rules. You'll want to write that down. I skipped number 24, didn't I? Oh, it's down there. Number 24, evaluate this. Now, when you look at your log rules, it usually looks like this. So you got to be wondering, hey, what's my exponent? Where's the equals sign? So you should write it equals x here. Now this is in log form. Now convert that to exponential form. So the base is 2. The power is over here. That's x. And the answer is the number right next to the base in log form. So it's 32. So you could guess and check this. Or maybe you know the powers of 2. Otherwise, you could actually not converted to exponential form. Whenever you see this, folks, you'll want to write down your change of base formula. But you could actually punch this into the calculator. Log of 32 divided by the log of 2. And either way, you'll get x equals 5, because 5 to the power of 2 is 32. What is the inverse function of log base 2 of x? So the first thing I like to do is change to exponential form. So my base is 2. My power is y. And if you like to write the equals y over there instead, that's good. So the base is 2, the power is whatever's over here, and the answer to that is whatever this is. Now, do the inverse, which means switch x and y. So 2 to the x equals y. Notice I switched the x and the y here. And so that means I know that the inverse function is y equals 2 to the power of x. Rewrite this in log form. All right, so my base goes down here, that's 5. The answer goes next, and the power goes after the equal sign. What is the approximation of log base 12 of 250? So you know that would really be like saying, hey, 12 to what power equals 250? That's a messy problem. You'd have to start guessing and checking. The powers of, or the multiples of powers of 12, don't hit 250. So what you can do is that change of base instead. You can do the log of 250 divided by the log of 12. It's going to be a really small number. 12 times 12 is 144. Then 144 times 12, so 12 to the third power goes way past 250. That's into the thousands. So it's going to be like 2 point something. Expand this. You'll want to look at your log rules here, folks, but I'm just going to focus on this part first, right here. Now this is all log base 3, so I'm going to write log base 3 a lot when I expand this. So it's going to be log 3 of 2. Now when I expand it, I change multiplication to addition. So log base, so plus log base x, and then that power goes out in front for log x. Now when I see division, that means subtraction. So then I'll have log base 5 plus, log base 3 of 5. Ooh, that needs to have a base 3 as well, my bad. This y is going to be log base 3 as well. And that 3 out in front, oop, that 3 needs to squeeze out in front. When I say that 3, I mean this 3 right there. There we are. Wow, that's a large